Okay, so this will be our last video for Chapter 4 for Math 1560, Calculus 1 at U of L for fall 2017. Um, so in this video we're going to look at error estimates for Taylor polynomials. So we want to investigate the question of when you choose a Taylor polynomial to approximate a function, um, what is the cost of doing so? So we know that the reason that we want to use a tailored polynomial to approximate some function, if our function is something like a trig function, exponential function, logarithmic function, or maybe even something more complicated, is that polynomials are relatively straightforward objects to work with. Polynomials are not that hard to use, um, whereas other functions, can't necessarily be computed exactly. We can't compute exact values for trig functions except at certain special points. Um, so when we switch from the function to the polynomial, because the polynomial is easy to work with, there's a cost. The cost is that the polynomial is only giving us approximate values. We want to know how good that approximation is. And so to measure the kind of quality of our approximation, we look at this remainder term, right? So another way, the reason we think of this as the remainder, right? It's the difference between the function and the polynomial. We could also think of this as, well, the function is given by the Taylor polynomial. If you rearrange this equation, the Taylor polynomial plus some leftover, right? There's some leftover part. Um, And and so there's a lot of analysis that you can do looking at this remainder term. There are a number of things that you can do, and one of the things that you would do uh, in maybe a third course in calculus, somewhere with something where you do sequences in series, is you start looking carefully at these remainder terms, and you look at what happens when n gets really big. And because one of the things that you're interested in calculus 3 is you're looking at we want to actually go from approximation to getting something like an exact expression for a function, but expanding in terms of powers. The problem is that you need to take infinitely many terms to do so, and one of the things that you would need to check there is that this remainder goes to 0. Right? So we want to kind of have this idea that as we add more terms, the approximation gets better and better and better. So as n goes up, the size of this remainder should go down. So frequently we're looking at the absolute value of the remainder. We want to see if we can make that small. So if we want to get some measure for this remainder, we have to know how to calculate it. Fortunately, this is something that was figured out by Taylor and by others around the same time. So Taylor's theorem, which is attributed to Taylor, I'm not sure that Taylor was the one that actually came up with the proof, but Taylor's theorem gives a formula for this remainder. The only problem with that remainder formula, it's sitting right here, as you can see. The problem with that formula is that it's given in terms of an integral. We don't know how to do integrals yet. We haven't defined integrals. So we don't really know how to work with this version. Fortunately, there is another formula for that remainder. There's actually about 3 different formulas for the remainder, but the one that's easiest to work with for us with the tools that we have at the moment is what's called Lagrange's formula for the remainder. So Lagrange's formula says if you want to know what this remainder is, right, you've calculated your polynomial up to degree n, so you've looked at the first n derivatives. Lagrange's formula says you look at the next derivative. You look at the n plus first derivative, right? So this is the kind of next derivative, right? After the last one that you considered when you constructed your polynomial. So you go up to say you're doing the degree 5 polynomial. So you've done 5 derivatives to calculate your Taylor polynomial. You do one more. And Lagrange's formula says that there's going to be some number c, and it's kind of like, the mean value theorem or the intermediate value theorem. We don't necessarily know what this number c is going to be, but there's going to be some number c in between the point where you're kind of centering your approximation and the point where you're evaluating, so between a and x. Somewhere between those two numbers, you choose this c, and you get this value for the remainder. we'll see that for the purposes that we're going to use this remainder formula, the fact that we don't know what this number c is, it's not going to matter. So let's look at an example so we see how we would work with this. So we'll do something simple. Let's say we're looking at the Maclaurin polynomial, right? So remember, for the Maclaurin polynomial, that means we're expanding about a equals 0. We're going to use the exponential function. So this is one where we've already done the Taylor polynomial. We looked at this one in class. We saw that the degree 7 polynomial is given by 1 plus x squared over 2 factorial. I'm not going to write it all the terms all the way up to x to the 7 over 7 factorial. Okay, so that's our polynomial, right? And we want to kind of know, well, what's the value of e, right? So what is e? E is f of 1, and we want to approximate this with p7 at 1, right? So that would be doing 1 plus 1 more plus 1 half, and so on up to 1 over 2 factorial, up to 1 over 7 factorial. I'm not going to calculate those values, but you could punch those into your calculator if you want. You can add them up. You can see where you get. And you'll find that actually it converges fairly quickly to the correct value for E, right? E is, it's 2.71, something like that. And so, you'll get, well, if you only do one term, you just have 1. You add the next term. Now 1 plus 1 is 2. You add a half. Now you're at 2.5. The next term, 1 over 6, you're adding about, what, 0.17 there. So you get up to like 2.67, right? When, so here's kind of pk for k equal to 1, 2, 3, 4. We go up to 5. 1 over 4 factorial. 1 over 24 is what, like 0.04. And so, yeah, actually by degree 5, you're already at like 2.71 something. You've already got the first 2 decimal places by the time you hit degree 5, right? So when you get to degree 6, degree 7, you're working on the 3rd, 4th decimal places. So if we want to know exactly what the error is, we want to, and again, we're just trying to roughly get an idea of the error, right? It says estimate the error. So we look at the remainder term. What does the remainder term look like? So R7 at 1. Okay. So let's come back. Here's our remainder formula. So in this remainder formula, we're setting, what are we doing? We're doing, for our example, a is 0, x is 1, n is 7. Okay. So we're going to get the 8th derivative at some c, okay, over 8 factorial times 1 to the 8. So that's what we get. We get this. We get the 8th derivative evaluated at 1, 8 factorial, and then x is 1 to the power of 8. Okay, so now you can see where you kind of can work this out. You can say, well, I know what the 8th derivative is. 8th derivative is still e to the x, right? So the 8th derivative at 1 is e, okay? And of course we don't quite know what e is. Well, we're trying to estimate it, so we can't use the value of e in our estimate. I should say here, right? It's not at 1, right? It's at some c, and I don't know what c is. So what I really have here is e to the c. And what do I know about c? C is somewhere between 0 and 1. Okay. And so then I know that, well, e to the c is somewhere between 1 and e. And, I can say, well, there are ways of convincing yourself that e has to be smaller than 3. So e is less than 3. Okay. So that means that my remainder, R7 at 1, it has to be less than 3, because that we worked out that has to be less than 3. 3 over 8 factorial. Okay, so that's what? That's 3 over 1 times 2 times 3 times 4 times 5 times 6 times 7 times 8. And I guess I could cancel those 3's, right? That's already a pretty big number, right? 5 times 6, that's 30. 7 times 8, 56 times, and then the rest we've got 8 more, right? So like 240 times 56. Well, let's pull it out. Let's see what we get. Okay, so calculator. 1 times 2 times, we skip the 3, 4 times 5 times 6 times 7 times 8. Okay, 13,440. And if we do 1 over that, okay, so we get 7.4 e to the minus 5 scientific notation, 5 decimal places, right? So this is, so we get a remainder which is less than 0.1234744. Okay, so that tells us that, well, we might be still off by some rounding error in the 4th decimal place, but we've got it up to 3 decimal places, definitely accurate. Maybe if we add one more term, then we've got that 4th decimal place nailed down. So it's a pretty good estimate, right? So now this was